Okay, everybody. So this week we're going to start fitting our concepts together. We'll start out by pairing t-tests and confidence intervals and showing how those two things really fit together. So to look at our chart now, we're still in the parametric tests. Over here, if the categorical factors, one independent factor with two levels, and you would end up using a t-test for that. So early in the course, we learned about how using the standard error of the mean and the t-distribution, you can generate a confidence interval. Basically, the idea that the true mean is within has a certain likelihood of being within a certain distance of your x bar and your sample standard deviation. We also learned that when you have population parameters, your confidence interval can be calculated using the z-distribution. So if you know the true mean and you know the true variance, then using the z-distribution, you can get the likelihood where, given a sample size n, the sample means might fall, right? And conversely, if you know the sample statistics, then your confidence interval is telling you in some likelihood, 95% confidence, 95% likelihood that your true mean is within some standard error of the mean of x bar, right? So if you have your population parameters, it will tell you information about where your sample might be given a given n. And if you have your sample statistics, then confidence intervals are telling you about where the true mean might be, right? So this is more useful, right? Because you usually start out with your sample statistics and you end up wanting to find out what the true mean of the population is. So yeah, what does the confidence interval tell us? Your confidence interval tells you where some chosen percent of your true means will be in relation to your sample means, right? So for example, with an n of 10 and a p equals 0.05, your t-distribution confidence interval would be negative 2.22 t or 2.22. So negative 2.22 times the standard error of the mean, or up to 2.22 times the standard error of the mean, plus or minus, right? Within this range, there's a 95% chance that you will find the true mean of this given sample, right? So 95% of the time, your true mean will fall plus or minus 2.22 standard error of the means of x bar. So we have this pretty well established. I think everyone has a firm understanding of this. Okay, so t-tests are basically just confidence intervals with hypotheses. The one sample t-test is the simplest, and they're very similar to confidence intervals. So the one sample t-test asks, does a sample come from a population that has a mean equal to some value, right? So the null hypothesis here is that the sample was taken from a population with this mean, hypothetical mean. And in this case, the mean of the sample would be equal to the hypothesized mean. And the alternate hypothesis is that the sample has a different mean than the hypothesized mean h. So in this case, the mean of your sample is not equal to the mean in your hypothesis. And so an example of that would be, is a sample of a tie lengths with n equals 10 and x bar equals 10 inches and a variance of 1.5 inches, is this significantly greater than a factory goal of 9 inches? So if we know that the population mean of things that come out of the factory is 9, would this sample have come from this factory, right? So the null hypothesis is that the sample mean is 9. The alternate hypothesis is that the sample mean is not 9. Or another example would be the population mean of all tie lengths produced at a factory is 9 inches. You own 10 ties with an average length of 10 inches and a variance of 1.5. Did you get your ties from the factory? This is kind of just a rewording of what I said above, right? And again, the null hypothesis is that the ties are from the factory. The alternate hypothesis is that the ties are not from the factory. The sample mean is not 9. Okay, so now we can compare the t-test, which has these hypotheses, with the confidence interval, which has this equation. And the question becomes, what is the t-score of our hypothesized mean for a sample with a mean of x bar and a variance s, right? So that's for this hypothesized value, this hypothesized mean, what is the confidence interval with the mean of x bar and a variance of s? So essentially it's solving for plus or minus t, and then saying that equals your confidence interval minus x bar over s over n. So your sample statistics are here, right? And then your confidence interval is set in this case by your hypothesized mean. So rather than finding a preset, 95% confidence interval, in this case, we're going to find what the t-statistic is for our hypothesized mean, right? So hypothesized mean minus our x bar, rather than having a preset thing in mind. And so this is what the t-statistic is for a t-test. It's just x bar minus your hypothesized mean divided by standard error of the mean, right? So just resolving your confidence interval, you can end up with your test statistic for the t-distribution that's going to help us with these hypotheses. So if we revisit our example of having as a sample of ties with an n of 10, x bar of 10, standard deviation of 1.5, significantly different from the factory goal or factory mean of 9 inches, right? The null hypothesis would be that the sample mean in this case is 9. The alternative hypothesis is that the sample mean is not 9. For a t-test, what we're going to be doing is taking this sample mean of 9, finding its t-statistic, and then finding a p-value for that, right? But for a confidence interval, you start with an alpha or p-value. You find a t-statistic, and you use that to calculate a confidence interval. So it's the exact opposite process of what you're doing for a t-test. So in this case, our t-statistic for the t-test comes out to be 9 minus 1 with our variance plugged in here and our number of samples plugged in here, so it's negative 2.1, right? And so then we bring it over to our R function that gives us the probability in the tails of the t-distribution for this particular t-statistic. So for negative 2.1 with the degrees of freedom of 9, the amount of probability in the tails of this t-distribution is 0.0325. Because it's two-tailed and we need not just this tail but the other tail, we multiply that by 2, and that gives us our p-value for this particular t-test, which is 0.065. And since 0.065 is above 0.05, right, we will fail to reject the null hypothesis, right? We can't say definitively that this sample has a different sample mean than 9. 9 falls within the 95% confidence interval here, right? Because p equals 0.05 is the 95% confidence interval, right? But we're at p equals 0.065, and therefore we're within that. If you have p values lower than that, then you end up rejecting the null hypothesis and saying that there's a difference, right? So if we did this the opposite way, right, and we wanted to calculate the 95% confidence interval, we would use our quartile function for the t distribution, put in our where we want our 95% confidence interval to be, right, with a degrees of freedom of 9, and we would come up with a t statistic for the confidence interval of negative 2.26 to 2.26, right? And you would end up multiplying that by the standard error of the mean to find the actual confidence interval. But this alone, we can see that our t statistic for 9 falls within the 95% confidence interval t statistics that we would be using to generate the confidence interval, right? So we can already see that generating a confidence interval would also show us that this proposed mean of 9 is within the where 95% of the means would be for our sample with an x bar of 10 and a standard deviation of 1.5. So this is the t-test and the confidence interval forward and reverse. Okay, so two-sample t-tests are also just confidence intervals with hypotheses. For a two-sample t-test, it's similar, but a little bit different, and it's because you're comparing two samples. You're not just comparing one sample to a hypothesized mean. So in this case, we have to account for a few things. One, we might have to account for the two samples having differences in sample number, and if the variances are unequal, we're going to have to account for unequal variances. Yeah, I know we said that this is in the branch where homogeneity of variances is needed, but we have a workaround here. So this is one case where you can have heterogeneous variances and still proceed with a t-test. So our question we're going to be asking here is the mean of the population from sample 1 different from the mean of the population in sample 2? Right, and so the null hypothesis is that the two means are going to be equal from the two samples, and the alternative hypothesis is that they are not equal. So our example is we would have two sets of ties with these particular statistics, right? One has a mean of 10, one has a mean of 9. Variance like this, variance of 1.5 and 2, numbers 10 and 15, right? And then our null hypothesis would be that sample mean number 1 is equal to sample mean number 2. An alternative hypothesis is that sample mean 1 differs from sample mean 2. All right, so let's explore this example in detail. The first thing you have to do is use what we know about testing for homogeneity of variances. So we're going to use the Bartlett test to see if there are homogeneous variances here. And usually this would be a division point for what we're about to do next. I'm not going to test this for heterogeneity of variances because I'm going to show you what you would do both if they were homogeneous or heterogeneous. So I don't really care which one it is. You will care because this will tell you which branch you're going to take in this next step. So if they're homogeneous, you're going to use this t-statistic equation. It's very familiar to the other, similar to the other one. You're taking the x bar of 1 minus the x bar of 2, so the difference is on the top, and you're dividing it by this nasty looking thing on the bottom. And so this nasty looking thing on the bottom is equivalent to your sort of a pooled standard error of measurement. And what it's trying to do is account for the fact that you might have different numbers of samples in one of your samples versus the other, and then weight the variance that is from a sample with a larger number more highly than the one from one that has a smaller number. And so what you'll ultimately end up doing is getting this pooled variance down here, and then putting it in the denominator of this top equation to calculate your pooled standard error of measurement. Right, and so I've calculated that out here using our example, and we end up with 1.82 after we do this pooled equation. Multiply it with to find our standard error of measurement, divide 1 by that, and 1.34 ends up being our t-statistic. So just like the other one, in the prior one tail, we end up with a t-statistic. If it's heterogeneous, we end up with this equation. Looks slightly simpler to execute, kind of is. And if you have heterogeneous variances, you can execute it this way, and they give pretty similar t statistics. The closer that the two variances are to each other, the less different they are, the more these two things will be almost the same. And the closer your two sample numbers are to each other, the more these will be exactly the same. But it's very important to use this top one if it's homogeneous variances, and the bottom one if it's heterogeneous variances. Okay, so now let's look at degrees of freedom for these two things. So if your variances are equal, you have homogeneous variances, your degrees of freedom are equal to n1 plus n2 minus 2. So for the one sample, it was minus 1. It was your number of samples minus 1. Here, because we're calculating a pooled variance, we're calculating two different variances, we're going to be losing 2 degrees of freedom since we're doing that equation twice. If your variances are not equal, the degrees of freedom is more complicated. It's this super nasty equation that you'll end up having to do. So in this case, for homogeneous, your degrees of freedom are simply 15 plus 10 minus 2 equals 23. For heterogeneous, this comes out to be 22.6. Okay, so for homogeneous variances, now we're going to calculate our p-values. So we go back to our function pt, which is going to give us the probability or integrate the t-distribution in the particular tail that is less than this t-statistic. I'm making them all negative just so that because r always integrates from left to right, for the t curve, it's easier. It will show you what's in the tails if you use a negative number as opposed to a positive number. So I say our t statistic is 1.34, so negative 1.34. Our degrees of freedom is 23. This gives us a p-value of 0.105 for one of the tails. Since it's two-tailed, we multiplied that by 2. And so 0.194 is going to end up being our p-value for this particular two-sample t-test, right? And so that's not significant. You would fail to reject the null hypothesis, and you would say these two are possibly having you can't tell that these have two distinct means, right? It's very possible that these are two samples from the same population. So if we compare that to how we calculate a 95% confidence interval, right? If we were calculating a 95% confidence interval here, we would start out with our QT function with a degrees of freedom of 23, right? And this would give us a 95% confidence interval in t-scores from negative 2.06 to 2.06, right? And we can clearly see that our t-score of 1.34 is well within the 95% confidence interval, which would also indicate that there's no significant difference between the two populations. So for heterogeneous, it comes out quite similarly. We have our t-score of negative 1.42, gives us a p-value of 0.084. Since it's two-tailed, again, we multiply that by 2. 0.17 ends up being our p-value, and that's not significant, right? And so if we compare that to calculating our 95% confidence interval, the only thing different here would be the fact that we have 22.6 degrees of freedom, thanks to our funky equation, and 1.42 is well within the 95% confidence interval there as well, right? So you can see that the two-tailed t-test also strongly resembles calculating a confidence interval, except you're rather than choosing your alpha, right, you're starting out with a chosen prediction and then backtracking to find a t-statistic. Okay, so next we're going to talk about paired sample t-tests. So paired sample t-tests are exactly like the two-sample t-tests, but with a small twist. So in a t-test, we compare two means with potentially two different standard deviations, depending on whether it's heterogeneous or homogeneous. So if we have one set of data here in blue and one set of data here in green, our t-test would be comparing the two population means using their parameters x bar and their standard deviation to try to tell whether or not the two population means are different from each other. But in a paired t-test, we add another piece of information. We determine whether the difference between paired measurements is 0. So if each one of these measurements was the same thing that was measured twice at two different times, right, then we have another piece of data. It's not just things measured here and things measured here. It's this thing measured being here and then this thing also being measured here. And so we can calculate the difference between the two measurements as opposed to just the means of the two measurements. And as you can imagine, this is very useful for the type of experiment we do repeated measurements, which we discussed earlier in the course. So the question we have in a paired sample t-test is there a difference between the two sets of measurements? The null hypothesis here is that there is no difference between the two, that the mean of this difference is 0. And the alternative hypothesis is that the difference is non-zero, that there is a difference between the two. So let's compare the two. For a regular two-sample t-test with homogeneous variances, you'd end up with an equation that looks like this. You have your difference on the top, you have your equation for pooled variances on the bottom. But for a paired two-sample t-test, now on the top you have this x bar of the difference divided by the standard deviation, the standard error of the mean using the distance, right? Standard deviation of the distance divided by n. So if we have standard deviation divided by square root of n, right? So the big difference here is that this pooled variance is going to use the x bar and the pooled variance is going to use the standard deviation of sample 1 and the standard deviation of sample 2, whereas this SD down here is the standard deviation of the difference, and x bar is the x bar of the difference, where up here it's the x bar of sample 1, x bar of sample 2. So this gets the main difference is this difference that's used to calculate the standard error for the paired two sample. This gets pretty apparent when you take a look at an example, right? So say we have 10 ties. We want to determine whether they will shrink in the wash. We measure their length pre and post wash. Are they significantly different in length, right? So we have our pre-wash ties with a mean of 10 inches and our post-wash ties of a mean of 9 inches. And I just now realized that I've made ties for lemurs or something very small because humans do not wear 10-inch ties, but that's fine. We have our ties that go from 10 inches to 9 inches, right? And so if you're using a regular old t-test, you would have 18 degrees of freedom because you have 10 samples in your pre, 10 samples in your post. You'd calculate your pooled standard error, you'd calculate your difference, which is 1, and you end up with a t-statistic of 2.26. But for a paired, you're now using these values, right? You're using the mean of the difference, which is 1, and you're using the standard deviation of the difference, which is 0.82, right? And so this is the standard deviation of these differences. And you can see right away that the standard deviation of these differences, 0.82, is much smaller than the standard deviations of either the pre or the post wash, right? So because the standard deviation is smaller, that's going to mean that our standard error is smaller, and our degrees of freedom are less. We have 9 degrees of freedom. All right. So ultimately, this leads to a larger t-statistic, which should translate into a smaller p-value. So that's the big difference here. We're using this difference column as opposed to the two statistics for pre and post. And so you can really see the difference here when you calculate your p-values, right? So we take our calculator in R that takes our t statistic and turns it into a p-value, multiply that by 2 to get the two-tailed significance. It is significant with two-sample t-test. There's a significant difference between the pre and post-washed ties. But for a paired t-test, now our p-value is much smaller, right? It's 0.004, so it's more significant. We are more likely, we're more able to discern between these two populations with our paired t-test than we were with our regular two-sample. So whenever you have a paired, wherever you're able to do a paired test or set up an experiment where you're able to measure something repeatedly, you'll end up with a greater ability to tell the difference between those two time points, which makes sense, right? You've added another piece of information. You've added the fact that now there isn't variance from sample to sample. You know that this sample was here and is now here, right? It was high, it is now low, or it was low and it is now high, right? The same sample, you've eliminated some amount of variance by tagging the same sample twice. So that's the difference between a regular two-sample and a paired t-test. We're going to put all this into practice in our workshop this week. So yeah, good luck with that.